So please welcome Jibu and Yu-Ting.
Good morning, everyone. Myself, Jibu Palathanam, and this is my colleague, Yu-Ting. There's one name here that we would like to mention. One of the main contributors to this work was Mr. Ajay Gupta. Unfortunately, he couldn't be here with us. So I'm just taking his place to present the work that we did at Ford. So today we are going to talk about mainly node count analysis that we did for 10Base-T1s networks. The presentation is divided into two sections. The first section would be mainly on the electrical analysis of the signal integrity testing that we did on higher node counts. And the second part would, Yu-Ting would take over to talk about the software latency. Just to give a brief background, as we know in the 10Base-T1s multi-drop network, there was, as the standards were defined, there was a limitation, not a limitation, but an assumption placed for 8 nodes, at least support of 8 nodes up to 25 meters. And at Ford, this was one of the analysis that we wanted to expand on, as this was considered to be lesser in number of nodes that we want, because as our network topology grew, the number of ECUs would be increasing. So we wanted to see what was the limit to the node count on a 10Base-T1s multi-drop network. So as we analyze the system, so one of the major factors that we see that affecting the node count was the electrical signal quality. As we did, we figured out that the electrical signal quality was the main factor contributing to the node count analysis. And so one of the major factors affecting the node count for the signal quality was the phi transition time, the rise and fall time of a phi of the signal, the external EMC noise, the overall system and node capacitance, and the node-to-node distance. So these were the four major contributing factors to the node count analysis that we did. And so as any testing, we needed to figure out what would be the acceptance criteria. And then for our signal integrity, we took 2 terms from the Open Alliance System Implementation Spec, which is the eye height and jitter. So we basically evaluated our networks and setups based on the eye height and jitter of the signal. So in our, as we go into these 4 factors, I'm going to go a little deeper into these 4 factors. And one of them, the first 2 factors are rise time and fall time and the EMC noise. So any phi has a rise time, the signal has a rise and fall time. And what we've understood from that is that, as per defined by the spec, the phi has to be within 15 nanoseconds. So what we are seeing is that higher, faster transition times causes ringing in the signal. Also, slower transition times have much lesser ringing. And so this is one of the factors that will contribute to the phi's rise and fall time. The second factor is the external EMC noise. Obviously, in an automotive environment, we have a lot of EMC noises that affect our signal integrity within the vehicle. And so what we've seen is that in our typical use case, approximately based on the EMC noise, we could see around 200 millivolt peak-to-peak voltage closure of the eye in our typical EMC environment. So these are the first 2 factors. And then if you go to the third factor, the node capacitance, obviously the node capacitance can be built up of many different components. One is the ESD component, the common mode chokes, the phi itself, and the trace. So we've attributed, we budgeted some of these capacitance value for each of these components. Again, the ESD would be less than 1 picofarad. The common mode chokes somewhere less than 10 picofarad. That's what we've defined for our systems. The phi can be less than 9 picofarad. Again, it all depends on vendor to vendor. We've seen differences from different vendors for the 10Base-T1s phis, where the capacitance for the phi itself can vary. And the trace obviously is 1 picofarad per inch. And so we've assumed, or we've come up with a number of between 18 to 25 picofarad is what we would say is the node capacitance that we would be aiming for. And as we know in IEEE, when the standards were defined, the 8-node count was based on the assumption that we have a 25 picofarad node capacitance. The next factor that we are going to look into is the node-to-node distance. So obviously, when we have multi-drop network, we have more nodes that are daisy-chained to each other. And so in our setup, what we've done is, based on two setups, setup 1 and setup 2, the setup 1 is all the nodes are equidistant from each other, whereas setup 2 we have one node that is further away. And what we've seen is that the node that is further away, or the setup that has, or the topology that had the node that was further away, yielded better results in terms of eye height and jitter. So this was basically contributing to the stack capacitance, or in sometimes the vendors call it capacity density of the system itself. And so these were the main 4 factors that keep contributing to the node count analysis. And what we've understood from as an OEM perspective is that the last 2 factors, basically the node capacitance and the placement of the nodes, are the ones that OEM have in control. So obviously the phi selection, the distance on our topology is something we can control as an OEM as we are designing a network. But obviously the other 2, the EMC noise and the rise and fall time, is again very dependent on the environment and the vendor that we pick. And so in our labs, what we did is that we basically used these 2 parameters to basically define what we would see we could expand on the limits. And basically by the system capacitance, what we did is we increased and decreased the node count by increasing the distance between them, and the node-to-node distance, obviously the segment length we increased. And so this is the varying measurements that we will go a little more deeper in the next couple of slides. So in the first comparison that we are going to show is basically, this is just a baseline. We wanted to get obviously a baseline of what the setup was. So we just kept on increasing the number of nodes. We had 8, 10, and 12, and 15 nodes. All we did is we just kept increasing the number of nodes, all equally placed 0.75 meters away. As you can see, the end-to-end distance just kept increasing. So this is the first first comparison setup that we have. And what we see in our system, the analysis that we did for the signal integrity, the maximum eye height, as you can see, as you increase the number of nodes without doing any limitations on the capacity or the system node capacitance or the node-to-node distance, as the number of nodes increases, the eye height also decreases. So we have in our limitation or define the spec, the eye height should be maximum of greater than or equal to 500 millivolt peak to peak. And as we see that as we increase the number of nodes, the eye height measured at each of these nodes, we took 4 measurements of far end, the 2 far ends and the 2 middle nodes, and we can see that the eye height greatly reduced. The same effect had on jitter also. Jitter is basically the 15 nanoseconds, the crossing over of the plus or minus 30 millivolt that we see in the eye diagram. And as we can see that as we just increase the number of nodes without putting any criteria on the limitations, the jitter also kept on increasing. Again, it was still within the 15 nanoseconds, but again, it kept increasing from what it was originally from the 8-node setup we had. And so we took this and expanded on this. So in our next comparison, what we did is we kept the end-to-end distance the same, meaning we took an 8-node setup and a 10-node setup, and the end-to-end distance was the same. But what we did is we increased the distance between the segment 1. Basically, if you look at here, the segment 1, we increased it for the setup 2 to be 17 meters, and the other, on a 10-node setup, we increased it to 21 meters. but everything else we left it at 0.75 meters. But if you look at here, the end-to-end distance in both these cases were the same. So this was to prove the node capacitance effect on the signal integrity. So as you spread it out, what would be the effect of the node, the system signal integrity? And what we've seen is that as we spread out the nodes, at segment 1 or the node 1 measurement showed better performance for eye height and jitter values. So in a stacked up node, we could see that the effect of system capacitance on the setup. And in comparison 3, what we did is we kept the, we didn't keep the node end-to-end distance the same, but we kept, we spread it apart in the aspect of segment 1. So basically, we just kept on increasing the cable length, but we kept the segment further apart. So it was segment 1 was 3 meters, and everything else was 0.75 meters, and in setup 1, as we saw in our comparison, was 0.7. In this one, we saw, because of the increased length, we saw greater effect on the DC resistance loss, affected the eye height much more than the jitter. So in both these cases, we saw that definitely the end-to-end distance and the node capacitance had an effect on the system performance or the signal integrity. And based on this analysis, we came up with the conclusion for the node count. Basically what we are saying is if you have less than, again, taking into consideration of a node system capacitance of less than or equal to 20 picofarad, and that's what we are aiming for at Ford, we say that for an 8-node system, we should have a 0.5 meters or at least 0.5 meters node-to-node distance. 8 to 10, we can say we should have at least 0.75 meters. 10 to 15, 1 meter, and 15 to 20, 1.5 meters. And we haven't tested greater than 20, but again, this is sort of what we are aiming for, and we are hoping that this would support our analysis. And with this, I would give it to my colleague Yu-Ting to go on the network analysis.
Yeah, so we want to quickly go back. We want to use the PLC, and we use the 10Base, because the 10Base is between on the FD and the Ethernet. They also have the multi-draw. It's good to use on the zonal networking. So, and they also can use the Ethernet, like the 7 layer. So they can use the multiple protocol and provide the application to use, and they can have the much operation for the protocol. They also can guarantee use the PLC, and they can guarantee that each node have opportunity to send the message. So how to reduce the message, the latency on each node side? So PLC provide a couple of the way to operate the latency. The first one is we can have the one node can have the 2 or the multiple the ID. Another one they can use the burst mode is on 1. The opportunity they can send the extra the friend. They can send the 2 or 3 or based on the setting. They can send more friend. Another one is combined together. They also can reduce the latency. But how to do this one on a PLC layer? So the first study we have the A node. Each node have the same bus unionization. So we try to use the EC1. They can have the multiple ID, and also they have the burst mode. So it's very similar on the STD latency. It's a very similar thing. We cannot say which one is good, which one is bad. So it's very good for you to reduce the latency. But something interesting is here for the nearby network, the latency is a little bit increased. So we can go to the next start. Let's start is more close on the real use network, because we now have each node has the bus loading, same unionization. So some node have use a lot, some node just nothing to use. So we have sorry, to go back here. So that's when we have the EC1, they have use the multiple ID or the burst mode. We have also they can use together. So if you let use it together, we can see here it reduce more the latency, but also they have someone need to pay. So the nearby node need to pay the latency. So their latency will be increased. So it's more close the node, the latency will be increased. So if they're more far away, there will be a little bit not much for this one. So we have if we have the node, if the network have So this one, this one. Okay, it's this one. Go back. This one, go back.
That's back.
Okay. So now we have the same network. We have the two nodes have the multiple ID or the burst mode. So they also can reduce the latency. But if they have node 1 and the node 8, they also have the multiple ID or the burst mode. We can compare this one on the first one. They can reduce, but not much, because they can affect each other, because the someone will reduce the latency, but they will nearby node will be increase the latency. But the good news is, if they can reduce more, but they need to pay too much. So going back to how to configure the PLCA for the latency, the burst mode and the multiple ID, they also can reduce the latency. But when we configure the PLCA, we also need to think about the nearby node. We need to think about the whole network, not just only individual node, the bus unitization. We also need to think about the nearby, which one is the important thing to configure the PLCA with the network latency.
Yeah, so as we conclude the overall presentation's conclusion that we take away is definitely we can have more than 8 nodes. Again, it depends on the node capacitance and the node-to-node distance. So as we showed in our analysis and the table guidelines that we have, there would be a minimum distance between the node-to-node distance and the node capacitance that we would recommend. What we also definitely recommend is to have a signal integrity testing on the final topology at various points in the topology, just to make sure that the signal is behaving within the specified parameters. So definitely either through simulations or through actual measurements, we definitely recommend running the signal integrity analysis at different points in the topology. And also definitely as we increase the number of nodes, as my colleague had mentioned, there would be decrease in the latency, but then definitely it would affect the nearby nodes budgets. So that is something we have to keep in consideration. It is required, it is a balancing act that we require. So it is not, I don't think we can have a single formula that can fit all, but it will be definitely based on a use case and the need of the topology or the requirement of the OEM to decide what would be the what would be the analysis of the node count and the final budgets. With that, again, I do definitely acknowledge our colleague Ajay Gupta for his work, and yeah, thank you.
All right, thank you very much. So we'll open the floor to questions. I see Daniel's already at the microphone, and then you'll be number 2.
Okay, good morning. Thanks for the interesting presentation. Definitely some valuable information you derived there. I just have one question, if you can clarify one of the introductory statements you gave. If I understood correct, you said you as the OEM can determine the position of the nodes and thus the distance between the nodes, which has a strong effect as you have shown. And the other statement I got was you can specify the PHY to be used. And my question is, by that do you mean something like you will determine one specific PHY in your RFQs to the tier 1 and this one has to be used, no selection possible, no economy of scale selection possible for the tier 1 if we have better prices with competitors? Or do you mean something like a release list where you will step by step over time check that multiple interoperable devices will work and then the tier 1 supplier can select out of that list basically?
Yeah, definitely, good question. So as an OEM at Ford, we do have a qualified part list. So we evaluate every 5 vendors, at least what we have in the market, at least for the 10Base-T1. We do that for all parts. So we basically go through an EMC testing. We require the vendors to provide us, and then we will add those. As they pass the requirements, we will definitely add it to our supplier approved list. And then that is also given to the tier 1 suppliers that they can pick any of these files from our approved part list. But so that is specific to some internal testing and their EMC testing that the 5 vendors are required to do to get onto our approved part list.
Obviously. Okay.
Thanks.
Thanks, got it.
Yeah.
Okay, so thanks a lot for the interesting presentation. I have two questions.
Yeah.
The first one, it's about the testing. So I believe you did test with daisy chain and not with stubs.
Yes. Daisy chain, correct.
Okay, but you didn't test stubs? Or?
No. So we, at Ford, actually, we're not going through stubs, at least for the 10Base-T1s. Yes.
Okay, thank you. Second question, about the latency, just to understand it's between what and what?
Latency.
The latency is just for the transmission latency. It's based on each node side, the transmission. They have the queue, and they have if they have the on time to send, it's no latency. If they can have some delay, it's a latency for the transmission.
Well, it's between the transmission from one node to the reception at another node.
Yes, it's for the TS.
It is, okay, thank you.
Okay, more questions? Anyone?
Is there much difference in the signal integrity analysis in the lab versus on a real vehicle with lots of different things?
There would be, I mean, this is again done at a controlled environment, so we would expect it to be a little different based on, and so that is something that we recommend, and that's one of our guiding principles when we define a topology to actually do a real life on a prototype vehicles or a breadboard where we have different EMC noises introduced by different ECUs, so to do signal integrity at that level too. So definitely there would be differences, and that is why we are keeping this buffer so that even if there is external factors that can affect the signal integrity, it will still be within the limits for the PHY to decode the signal. Yeah, thank you.
And any other questions? All right. Just checking. Nope. Okay. Then thank you very much.
Thank you.